So next we have the definition of length of a vector v, which is written as this double line. Okay, inside these two double lines you have v, that's read as norm of v, is defined as the square root of inner product vv. Inner product of two vectors is the scalar. So we consider the inner product of a vector with itself. So suppose you have this to be say inner product of v to be say 4, then in that case square root of 4 you will have as plus or minus 2, but being length we'll have to consider the positive value. So it is when you have v itself to be 0, of course you will have it as 0. So this norm is always a non-negative number. Norm of a vector is always a non-negative number. So the next lemma is just the application of Ip1 and Ip3, and we had one remark. So just the application of those two, that we will have this. Now inner product of alpha u plus beta v with itself, or in other words norm of alpha u plus beta v square. So what is it? So that is what is explained here. We will consider, we can easily see it is alpha. When it comes out from the second place with conjugate, it has to come out. So alpha conjugate inner product u, and then alpha beta conjugate, because it is in the second place, when it comes out with conjugate it has to come out. So alpha beta conjugate inner product u with v, and then v with u. So that means beta alpha conjugate inner product v with u, and beta conjugate inner product v with v. So this is what we have to show. Now for convenience sake we shall take both are the same, but one we will retain as such, the other one we will write it as w. So that Ip3 when you use, that is linearity property, it is used. So you have this, and now you replace your w by this alpha u plus beta v. So you have this, and again because it is in the second place, when it comes out with conjugate it will come out. So u with u with v, so in that case beta conjugate. Similarly alpha conjugate, this beta will remain as such, v with u, and beta conjugate v with v. So that is our RHS. So as a corollary to this, when we have, see suppose your beta is 0, then you will have inner product of alpha u with itself. So this is norm square. So norm will be when you consider mod alpha, it is alpha conjugate square root. So and this one you will have inner product of, see actually it is like this, alpha u, inner product of alpha u with itself. This inner product is with itself, and that is square root of this you have to have. So alpha conjugate it will come out. So you have mod alpha square. So this will be mod alpha square. So here it is alpha conjugate mod alpha square norm u square. Therefore you have norm is always non-negative, so we don't have the negative sign here. Now we prove the next lemma, which will be useful in proving the Cauchy-Schwarz inequality. So this states that if ABC are real numbers with A positive and A lambda square plus 2B lambda plus C is greater than or equal to 0 for all real numbers lambda, then B square is less than or equal to AC. What is B? It is the coefficient of lambda divided by 2. B is coefficient of lambda divided by 2, and A is the coefficient of highest power, that is lambda square, and C is the constant term. So B square less than or equal to AC. So this is our target. Now what is given, we will consider A lambda square plus 2B lambda plus C. Now we are going to first take A out, and whatever is remaining we are going to complete the square. So when we do it, we will get it as A into lambda minus B by A the whole square plus AC minus B square by A square. Taking LCM, so all these three together only gives us this lambda minus B by A the whole square, plus this one gives us AC minus B square by A square. But a lambda square plus 2b lambda plus c is greater than or equal to 0 for all lambda. So for all real lambda. So in particular you can choose it as b minus, it should be b by a. You can choose it as b by a. So you have this here it is correct. This is minus only, but here it should be lambda plus b by a the whole square. Here correction is to be made, lambda plus b by a the whole square. So here taking lambda as minus b by a, this becomes 0, but already we know that this is greater than or equal to 0. This is greater than or equal to 0. So you have got this one to be 0 because you are choosing this as minus b by a. So this one will vanish. You will be left with this. A is positive, so you can even cancel that. You are left with AC minus B square, which is greater than or equal to 0, since that's because A is positive. So we get B square to be less than or equal to AC. We now proceed to an extremely important inequality called Schwarz inequality. So which states that if U and V are in the inner product space VC, even though it is just mentioned as V, we should remember that our V is an inner product space. So if U and V are members of an inner product space capital V, then modulus of inner product UV is less than or equal to norm U into norm V. So we are going to prove this in as 4 cases. One is both of them are 0. In the second case we have one of them to be 0, and the third case both of them non-zero, but the inner product is a real number, and in the last case we are going to have both of them non-zero, but the inner product is a complex number. So these 4 cases we will consider. In the first 2 cases it's very obvious that equality holds, for the reason that when U and V are 0, the right side is going to be 0 and even the left side also. And as for this one is concerned, if one of them is 0, then naturally the inner product is 0. So even in this case equality holds. Now in the third case we are considering inner product both U and V to be non-zero and inner product to be a real number. Now this we are going to consider. What is it? You consider a real number lambda in R and the inner product lambda U plus V with itself. So when we expand this, this is what we get, lambda U with this one. So mod lambda square into inner product UU, inner product UU, which is norm U square, and then U with V, so U with V, and then V with, this is in the second place. When it comes out with conjugate it has to come out. So inner product VU you are left with, and this one inner product VV. So here 2 terms altogether you have 4 terms, right? So mod lambda square norm U square plus this we can rewrite as inner product UV conjugate. This is by Ip1. So you can now rewrite this as 2 times real part of this. The reason is, you know very well that Z plus Z bar, when Z is a complex number, Z plus Z bar is nothing but 2 times of your real part of Z. That is x plus Iy if you take, then this will be 2x, so which is nothing but real part of Z. So if you take Z as x plus Iy, this is what you see. So that is what is written over here. So it is 2 times real part of, you consider the whole lot as some Z. So Z plus Z bar, which is 2 times real part of Z. So this is what we have. Now this is nothing but norm of lambda U plus V the whole square, which is less than or equal to. Why this less than or equal to? Because real part of Z is always less than or equal to modulus of Z. So we make use of this result from complex analysis and then apply that here. So you have this. So that is how inequality comes here. So far we had only equality. The inequality is because of this. So you have mod lambda square norm U square plus 2 times lambda into modulus of inner product UV plus this one is retained as such. So this one is greater than or equal to 0. This one is greater than or equal to 0, and therefore the whole lot is greater than or equal to 0. Now this is of the form A lambda square plus 2b lambda plus c. So by the above lemma, this should imply that b square should be less than or equal to ac. So you will have A to be norm U square and B to be modulus of inner product UV. So from here, this is my A, this is my A, and this is my B, and this is our C. So B square should be equal to B square should be less than or equal to A into C. So you have this, which in turn implies this. Now suppose you have U and V are non-zeros with inner product to be complex number. So when this is a complex number, naturally inner product U by alpha with V should be a real number. This should be a real number. So you have by the third case, we can have it as modulus of inner product U by alpha. We are applying this to these two vectors, which U instead of U and V, we have U by alpha V. So you have modulus of U by alpha inner product U by alpha V the whole square to be less than or equal to norm of this square plus norm of not plus into product, so it is product norm V square. So modulus of inner product UV the whole square is less than or equal to what happens to this mod alpha square? See, by the corollary, this has to be 1 by mod alpha square on the right side, but on the left side also you have 1 by mod alpha square. So we can cancel them and that is non-zero because U and V are non-zero. So you can have the resultant to be modulus of inner product UV to be less than or equal to norm U into norm V. So in all the four cases, we are able to establish either the equality or inequality. Modulus of inner product UV is less than or equal to norm U into norm V. As specific cases of Schwarz inequality, we have the following. The first one, we will consider V to be Cn. We will consider V to be Cn. So in that case, what will happen to my Cauchy-Schwarz inequality? It will become just because inner product UV we know very well from that example that it is nothing but summation alpha I beta I conjugate. Summation alpha I beta I conjugate I ranging from 1 to n. So we can just make use of that definition of inner product and use Schwarz inequality, so that now this same Schwarz inequality in the case of Rn, in the case of Cn rather, will become like this. So this is as for the application. Actually we can call it as an application in the case of Rn or Cn. So in the case of Rn means here this conjugate will not appear, otherwise it is the same. Now in the case of collection of all complex valued continuous function defined on the closed interval 0, 1, the inner product is defined as fg bar, that is integral 0 to 1 f of t g of t conjugate dt. So you just apply the Cauchy-Schwarz inequality and replace your u and v by f of t and g of t respectively. So next we have the triangle inequality, which states that if uv belongs to v, so for given any two vectors, norm of u plus v is less than or equal to norm u into norm v. Here we have just two, norm of u plus v. Norm of u plus v is less than or equal to norm u plus norm v. It is norm u plus v. So we consider norm of u plus v the whole square, which is inner product u plus v with itself, and we know to expand this here two terms, altogether four terms, and this is rewritten in this way. So we know that this is twice real part of z, that is inner product uv, and so norm of u plus v the whole square. Again the same result, real part of z is less than or equal to mod z, so using that we get this, and by Schwarz inequality this has to be less than or equal to this is double line, not triple, so norm u into norm v plus norm v the whole square. So this is of the form a square plus b square plus 2ab, so norm u plus norm v the whole square. So from which we get norm of u plus v is less than or equal to norm u plus norm v. See, in the case of Schwarz inequality, here you have product in the case of Schwarz inequality, but this is triangle inequality. So Don't mix up this with the previous one and write the new Cauchy-Schwarz inequality as modulus of inner product UV is less than or equal to norm U plus norm E. That's incorrect.